Welcome to the first video in the second unit of the semester, where we'll be talking about acids and bases. So this is a topic that you've discussed before, most likely in general chemistry, possibly in high school, and it might have come up in passing in Organic Chemistry 1. So in this unit, we'll first be reviewing what we know about acid-base chemistry, and then we'll be taking a step further to answer some fundamental questions about the nature of acidity, and we'll wrap up by actually discovering that understanding the acidity of compounds is a very helpful tool in understanding other types of reactivity as well. So to get started, I thought we could answer a simple question, or it seems like a simple question. Are all acids the same strength? You probably have already seen this on the screen as I've been talking, and you probably have an answer. That's okay, keep it to yourself for now. What I want to do first is define some terms, right? So are all acids? Well, what's an acid? And then the other question is, what do we mean by strength? Right? How do we describe that? How do we define it? It seems to be a characteristic of an acid, so potentially it's measurable. Right, so we'll focus on defining our terms first, right? So this is the part where we're going to do a little bit of review. So when we say the word acid, it turns out that it's a little bit ambiguous because you might have learned that there are multiple kinds of acids depending on how we define this concept of acidity. So normally, if you hear a chemist or a biologist, or I guess a biochemist, say the word acid, what they mean is Bronsted acid. It's typically what's implied. If we meant some other form of acid, like a Lewis acid, we would use the name Lewis to denote what we mean. So Bronsted acid is a compound that donates a proton. So you probably have heard this definition before, and you maybe memorized it for a Gen Chem class. I want to be careful. What we mean by a proton is a hydrogen atom that's positively charged. It's easy to confuse hydrogens that are uncharged or even negatively charged with those that are positively charged, so I just want to be clear about what we mean here. And if we use the word base, again, what we mean is a Bronsted base. If we meant Lewis base, we would use the word Lewis. And so this is any compound that you probably heard accepts a hydrogen. I don't like that language because accept is extremely vague, so I'm going to be a lot more specific. This is any compound that can form a covalent bond to a H plus ion. So a compound that can form a covalent bond to H plus. Well, we know a bond contains electrons, and one of the implications of this definition is that a base needs to have a pair of electrons that it can use to form this bond. So a base must have 2 electrons to donate. So based on this definition of a Bronsted base, we actually know something about the structure of any compound that we can describe as such, and that's that we need to have these 2 electrons. So that can come from a variety of places. This could be a lone pair. That's pretty common. You might think about things like ammonia, NH3 that's got a lone pair of nitrogen, that can be a base. Classical examples are things that are negatively charged with lone pairs, like OH minus, that oxygen has 3 lone pairs. It's not the negative charge that matters, it's the lone pairs. But it's not required that you have lone pairs to be a base. You actually saw an example of this in OChem 1 when you learned about additions to alkenes. So if you think about the mechanism of like HBr reacting with an alkene, you know that the first step is protonation of the alkene. Well, that sounds like the alkene, or the compound that contains the alkene, is acting like a Bronsted base because it's actually forming a new covalent bond to that H plus ion, but it's not using a lone pair to do it. It's using electrons in the CC pi bond to do it. So we could say that this is likely a lone pair, but it doesn't have to be. We can also use electrons in a relatively unstable bond. All right, so our source of these two electrons that a base is going to donate into a new bond with a hydrogen atom is usually a lone pair, but could be electrons in a relatively unstable bond. So we've defined our terms. We'll use the term acid and base. What we mean is this Bronsted idea, what we're talking about, either like putting an H plus into it or giving it to something else, or taking that H plus and forming a bond to it. So now that we have these definitions, we can actually look at an example where these definitions would apply. So we'll look at an acid-base reaction, where there's both an acid and a base that are reacting with each other. And so we'll use an acid that you're likely familiar with, HCl. I'm going to draw all the lone pairs in. All right, so I've got something like that, and then I'm going to use water as the base. You don't necessarily think about water as basic, but looking at its structure, the oxygen has two lone pairs, which is all that's needed for something to be a base. Any compound with at least one lone pair, in principle, can be a base. So if I'm going to be thinking about how this reaction works, because this is something you've likely already thought about, I bet you could predict the products here. So if we were to use our Gen Chem knowledge, we might predict that HCl is going to function like an acid. In fact, that's even in its name, hydrochloric acid. And if this reaction is going to happen as an acid-base reaction, that means the water needs to be the base. And then I can draw the products based on these definitions, right? So I know that HCl is going to donate H+. Well, there's only one hydrogen in the structure, so I know which one it is. And the base is going to form a new covalent bond to that H using one of its, I guess in this case, lone pairs. So we know that we're losing a lone pair on oxygen and forming a new OH bond here. Cl minus, or Cl is going to lose the hydrogen, but it's going to lose it as H+, which means the electrons in the HCl bond end up going onto the chlorine. We could even show that using mechanistic arrows. So we could show the oxygen lone pair forming a new bond to the hydrogen and the electrons in the HCl bond going to the chlorine. All right, so that means I've now got 4 lone pairs on chlorine. I know from my formal charge rules that makes the chlorine negatively charged. And I'm going to have an oxygen with 3 hydrogens attached. Only 1 lone pair, and my formal charge rules tell me that oxygen is going to be positively charged. Okay, so these are the products. Because chemists like to have really antiquated naming, we also call these compounds the conjugates. This is extremely old language that we've somehow never been able to get rid of. And one of the reasons that this is important to know is that these reactions are always reversible. Any acid-base reaction is a reversible process. It may not be very favorable to go backwards, but it's in principle possible, which means that these structures will be acids and bases that can transfer a proton to get back to this state. So if I just looked at my conjugates, and then I looked at what I would turn them back into, it looks like Cl- could use one of its lone pairs to actually accept a hydrogen into a new bond to the chlorine, and this oxygen would be donating that proton. So it looks to me like the chlorine in the reverse reaction is functioning like a base. And the H3O plus cation is functioning like an acid in the reverse reaction. Well, that's confusing. Now I've got an acid and a base and an acid. Like, if I'm talking about this reaction and you say something like acid, it's ambiguous. Do you mean this one or this one? So we actually add the word conjugate to these terms so that we know whether we're talking about the forward or the reverse direction for the reaction. So here's our conjugate base and our conjugate acid. Okay, so just one way to remember this is that conjugate, what we're doing is describing like the products of the forward reaction. If we're talking about like, well, how strong, for instance, is the conjugate acid, we would be implying something about the reverse direction. So it's important that you both know these terms, that you could assign these roles like base and acid to structures on the basis of these definitions, and also be comfortable with like the various ways that we talk about conjugates versus, I guess, the reactants, just the acids and the bases, right? So this is probably a review from Gen Chem, but it is important that you make sure that you're solid on this, because we're going to be talking quite a bit, it turns out, about the conjugates in the course of this unit. So in the next section of the video, now that we've decided what an acid is, and we've looked at an example and reminded ourselves of acid-base reactions, we'll try to address this question of strength, right? To get back to our original question, are all acids the same strength? So one thing that many students end up confused about after the whirlwind treatment that is acid-base chemistry and general chemistry classes is what strength means. I hear all sorts of things. Things like, well, a strong acid is a stable acid, or it's one that doesn't change, things like that. And nothing could be further from the truth. We need to think about this word strength in the same way we would think about in medicine. So you might have bought some Advil at some point, or Aleve, and maybe the bottle says extra strength. Well, what does that mean? That like the pill doesn't break up or doesn't dissolve in your stomach or what? Well, that would be pointless. Like, that would be like the reverse of marketing, right? Don't buy this product, it won't work. Instead, when we think about strength in that capacity, we mean that this concept of strength describes the ability of the compound to perform its role. So if we're thinking about Aleve, extra strength would mean even better at killing pain. Right, so we're basically saying the strength is a measurement of ability to do its role. We should write that down. Measure of ability to perform the role. So if we think about acid strength, I can't spell. You'll notice that almost every video involves me misspelling something on the board. We have first the role described, and then some notion of the ability of a compound to actually do the role. So if we're talking about acid strength, what we're basically describing is ability for a compound to donate H+. Right, so donating H+, that's the role described by acid, and then strength is this ability for the compound to do that. So, for instance, we could look at our acid from the earlier section of the video, HCl. If we thought about HCl in isolation, so not an acid-base reaction with water, but just HCl on its own, this concept of acidity could still apply. We could donate the H+ to the environment, right? So we might have a process that looks like this, probably reversible, where we just break apart the HCl bond such that the H is H+, and then both electrons in this bond end up on chlorine. So we'll have H+ and Cl- with 4 lone pairs, which I will draw, minus. So this equilibrium we call acid dissociation. In this concept of acid dissociation, there is no base. The proton of HCl is just being donated, and nothing is really accepting it. So if we're thinking about acidity as a role, this might be a good reaction to study, because we're not going to be confounding anything that we're measuring with like notions about what the base might do or might not do. This is just a solo act for the acid here. So maybe one way we could do this measurement of ability is to just talk about like where the equilibrium lies. So we can measure acid strength by assessing or measuring position of the equilibrium here of our acid dissociation. So to do that, we're going to define our equilibrium constant, so that's our capital K. And we could write like little c or little eq down here, which is fine. That's really, we always describe these acid-base, or any equilibria like that. But if we're talking about acid dissociation, we're going to use a lowercase a to basically make it clear to a reader, we're talking about a specific kind of equilibrium, this acid dissociation equilibrium, right? So we're going to measure Ka. So if we do this for HCl, we actually find that this is about 10 to the 6th. 10 to the 6th, which is, well, it's a number. You might remember that if this number for capital K is greater than 1, we have more products than reactants at equilibrium. So this number is, well, just a little bit greater than 1, by which I mean a lot bigger than 1. So once this acid dissociation reaches equilibrium, most of the HCl has been converted into H plus and Cl minus. There's only going to be a very small amount of HCl left, right? Almost everything dissociates. So if we think about this acid strength as the measurement of an ability of a compound to donate H plus, I think we could call HCl a very strong acid, because this equilibrium constant tells us that it basically does this role almost to completion and in its entirety, like almost no HCl is left. So what we can say is that as Ka goes up, that acid strength goes up. Right, so very large numbers of Ka, we're talking about like strong acids, right? So the converse would be if we had a very small number of Ka, like, I don't know, 10 to the minus 10th or something. These are very not strong acids. Another way of saying that is that they would be weak acids. So when you hear weak, it's still a measurement of strength, right? It's the opposite of strong, but the same kind of concept that we're talking about ability to perform a role still applies, yeah? And then the other thing that I would add is that we can also talk about a strong base or a weak base. What do you think that might describe? So pause your video. I want you to write a definition, like this one, for base strength. Hopefully you've had a chance to write your definition down. One of the things you'll notice is that the word strength is staying the same, but the role, base, is changing. So we're still talking about ability. That's really what we mean by strength. But now we're talking about the ability of a compound to not donate a proton, but to form a new bond to the proton. Okay, so this is a little bit different, and this is actually going to be critically important for how we use acid-base chemistry in this semester, and all through the semester, not just Unit 2. So this is a really foundational concept. If we're talking about the ability of a compound to form a new bond to H+, what we're really describing, when we get down to it, is the ability of the compound to use its electrons. Ability of a compound to use its electrons for a specific purpose, to form a bond. But if we think about this carefully, this ability of a compound to use its electrons to form a bond, that's more general than just being a base. We also could use notions of base strength as a measurement to actually predict or talk about nucleophile strength. Remember that a nucleophile is a compound that donates its electrons into a new bond. So this is kind of a place where acid-base chemistry we can use to predict other kinds of behavior for molecules. Because in some cases, what's happening in an acid-base reaction is analogous to what's happening in other kinds of reactions. Like, for instance, if an anion is a nucleophile or an SN2. It looks a lot like acid-base chemistry, it's just that you're aiming the electrons at an atom other than a hydrogen. So we'll take advantage of this pretty extensively all throughout the semester. But it probably feels a little bit uncomfortable now. And so in the rest of this unit, we'll be talking in great length about making predictions about acid-base reactions, making predictions about acid strength and base strength from structure. And then in the very end, we'll be starting to think about how we can correlate those features to other kinds of roles. In the final section of this video, we'll be circling back to our original question. Are all acids the same strength? Well, we're ready to answer this now because we've defined our terms. We know what acids are, or we've reminded ourselves of what acids are. And we've talked at length about this concept of strength as well as how to measure it using Ka values. So HCl, we've already discussed. We know that this is a very strong acid, and its Ka value is much larger than 1, about 10 to the 6th. But you can see some other kinds of acids here in this table that I've put up on the board. One of them is ethanol, and in particular this proton, which is pretty acidic relative to all the others. Again, acidic is a way of talking about acid strength. We end up with this equilibrium as shown, but the equilibrium constant is 10 to the minus 15th. So there's 21 orders of magnitude difference in acid strength between HCl and ethanol. All right, so clearly, no, not all acids are the same strength. And it's like not even close. Depending on the structures of compounds, we have radically different kinds of acidities. But, well, maybe like, well, all hydrogens attached to oxygens. Maybe those are all the same acidity because that would be convenient, but that's not true either. If we look at phenol instead of ethanol, if we remove if the proton dissociates from this oxygen, my Ka value is 10 to the minus 10th. So 5 orders of magnitude difference between the acidities of these two structures, even though oxygen in both cases is the atom losing a hydrogen or losing a proton. And then finally, we could really put a nail on this coffin of this other hypothesis. So well, it just depends on the atom that's losing the H. So here's acetic acid. This is in vinegar, right? So this is kind of the sour and a little bit acidic component of vinegar. So this proton comes off readily. So this is the acid-base equilibrium that's relevant for us. And you can see the Ka value is about 2 times 10 to the negative 5th. So we're about 5 orders of magnitude more acidic than phenol now. So 3 different like oxygen acids or oxygen atoms that are losing the proton, and we're spanning about 10 orders of magnitude in acid strength. So these are really big differences that are being driven by some kind of structural features that we're not necessarily ready to predict or understand yet, but that's really the function of much of this unit, is coming up with sets of structural explanations to actually rationalize why we're seeing such radical differences in acid strength. It turns out that the rationalizations that we come up with, like the structural observations that we attribute to these changes in acidity, those structural features will also drive almost everything else about the ways that molecules react. So understanding acidity and understanding what's driving acidity at a structural level is probably the most important skill in organic chemistry and possibly also in biochemistry, because it's a way of being able to talk about how structure influences or really dictates function. So the last thing that I want to do in this video is just to remind you of one other kind of measurement, or actually way of reporting a measurement, that we use to talk about acid strength, and that's pKa. So rather than a Ka value, we could also describe things as pKa's. So the pKa of a compound it's a mathematical manipulation. So it's negative log base 10 of the Ka value. So this is something you likely talked about in Gen Chem. Anytime you see lowercase p in chemistry, it means negative log base 10. So what we're going to do then is simplify these numbers. So we no longer have to talk about like 10 to that, and we're just going to have usually simpler figures that we can cite and in some cases, as we'll find out, memorize. So I'm going to give you the pKa values for these 4 acids as well. So for HCl, this is negative 6. For ethanol, the proton on the oxygen, this is about 15. For the hydrogen on phenol here, it's about 10. And for acetic acid, this will work out to be around 4.7. Right, so we'll say approximate. Not negative, approximate. So what I'd like for you to do in closing is, just like we wrote a statement, as Ka goes up, acid strength goes up. I want you to write a similar statement involving pKa. So as pKa does blank, acid strength goes up. So we notice that our strongest acid, HCl, by which I mean having the largest Ka value, also has by far the lowest pKa value. And our weakest acid, or the compound with the smallest Ka, has the largest pKa. So maybe annoyingly, our relationship's a little bit different. As pKa goes down and then becomes negative, our acid strength goes up. So this I want you to memorize. For almost the rest of this unit and semester, we'll rarely, if ever, talk about Ka values. Exclusively, we'll use pKa values, right? So this is really the relationship that you need to have dialed in your head. The only other thing I'll add here is the definition of a strong acid. So you probably were told there are like 5 strong acids in Gen Chem, and you were asked to memorize them, but maybe you were never told why we call them strong acids. It turns out there's not any agreement among chemists about exactly how to think about this, but a good working definition that many of us use is that a so-called quote-unquote strong acid has a pKa of equal to or less than 0. So anything that has a pKa of 0 or a negative pKa value, we would basically talk about as a strong acid. But as you can see in our table, maybe talking about a strong acid isn't all that useful. It's more like, is an acid stronger or weaker than something else, right? So we're really going to be focusing on comparisons here. Okay, so that concludes our first video. We've reviewed some basic topics in nomenclature about acid-base chemistry. We've introduced the concept of measuring acid strength and what that means. We've introduced the use of pKa values as a shortcut to talk about acid strength. And we've addressed this question. We know that there's apparently some important structural features that drive differences in acidities.